Okay, everybody. Well, as promised, this is the YouTube video of the stuff that we didn't finish today, Monday, the 21st of August. Um, it is thundering and lightning outside, and my dog barks at uh, the thunder and the lightning. So if you hear a dog barking or you hear a rumble of thunder, that's what it is. I'm not going to try to edit any of that out. That kind of thing just takes far too long. So this evening, we're going to finish up the material that we should have covered today in class. It actually was a lot of material, and so moving this to the YouTube channel so that you can view it on your own before class on Wednesday, I think will make a good use of our time. So we had just finished talking about ethene, and we had talked about the fact that there are sigma and pi bonds in ethene. Two carbon atoms with a carbon-carbon double bond, and one of those bonds is an sp3, or excuse me, a sigma bond, and the other is a pi bond, and each one of those carbons is said to be sp2 hybridized. And so if we think about that, sp2 hybridization means to take one s orbital and two p orbitals and hybridize them into three new sp2 orbitals. And in doing so, that leaves a p orbital unhybridized, and you have this this p orbital that's left over that can actually be used to form the pi bond. That's how we get a pi bond from p orbitals. And so if you think about the ground state of carbon again, we're not going to focus on the 1s electrons that we have here. We're just talking about the valence electrons. And we undergo some type of electronic promotion through the input of energy. We end up with it's not showing it, but one of the electrons from the 2s orbital needs to come up to the 2pz before hybridization. So note that one of these 2s electrons is actually being promoted into the 2pz orbital. I don't know why that's not showing up on my hybridization or my animation, so I apologize for that. And so once that happens and we hybridize, we're going to hybridize the 2s orbital with its one electron and the two of the p orbitals with their electrons. We're going to get three new sp2 orbitals, and that leaves the 2pz orbital where it was with its single electron in it. And so that's what happens when we form an sp2 hybridized carbon atom. And so the way that you can figure out hybridization pretty easily is simply, can you count from 0 to 2? And so if you look at a molecule, if you can count the number of multiple bonds, that is, if it has a pi bond or two pi bonds, you can readily determine the hybridization of the molecule. So for example, if your molecule has no multiple bonds, then you're sp3 hybridized. If your molecule has one pi bond, then you're sp2 hybridized.
Hello, please leave a message.
And if your molecule has two pi bonds, then your molecule, or your atom, I should say, is going to be sp hybridized. You can think about this, just write sp, sp, sp. And if you think about 0, 1, 2, then it's going to be 3, 2, 1. And you can figure that out pretty easy. And so if we look at an example of 2-butene, so this is an organic molecule. It contains only carbon and hydrogen, so it's a hydrocarbon, which we'll learn more about later. But you can see that the atoms in green are sp3 hybridized because this carbon atom has all single bonds to everything that it's bound to, so it has no multiple bonds, so it's going to be sp3 hybridized. However, if we look at this carbon, we can see that it's going to have, since it has a triple bond, it's going to have two pi bonds, and so two pi bonds is going to give me an sp hybridized carbon atom. So we've got sp3, sp, sp, and sp3. Okay, and this works well if a carbon atom meets the octet rule. Now we need to talk a little bit about structure and bonding. In condensed, we've got several types of structures that we're going to need to learn about. But so, for example, condensed structures are actually a shortcut. So if you imagine drawing this molecule, okay, so 4 carbons and 10 hydrogens, so it's a pure hydrocarbon. To actually draw all this out to show all the carbon connections and all the hydrogen connections will actually take quite a bit of time. Take a moment right now and try to do it on a piece of paper. It actually takes quite a bit of time. However, we can condense that down into CH3, CH2, CH2, CH3, which actually condenses that down and allows me to write this structure out without having to draw the lines. Now, this can be condensed even further by taking these 2 CH2s and actually combining them inside parentheses, where we would have the CH2 in parentheses with a subscript 2, telling me that I've got 2 of these so-called methylene units between these 2 so-called methyl units. And we'll learn more about the nomenclature later, so don't worry too much about it. So here we have the entire structure drawn out. Here we have it in condensed, and here we have it further condensed. Now it turns out that condensed structures still take quite a bit of time. So here's an example of a molecule known as hexane, so 6 carbons and 14 hydrogens. It's a pure hydrocarbon. So hexane, a lot of carbons, a lot of hydrogens. I can actually draw the condensed structure CH3, CH2, 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 CH3. That too takes quite a bit of time. However, we can use what's known as the skeletal structure here, which allows us to rapidly draw the hexane molecule and actually give it more of a real structure. So notice it's kind of zigzagged. This is actually known as the skeletal structure, and the reason that it's zigzagged is because each one of these carbon atoms is tetrahedral. As an example, if you wanted to get a bunch of tetrahedra, you can build these with your model kit and link them together, and what you'll find is you get a zigzag structure. Anytime you link tetrahedra in the corners, that's what you're going to get is a zigzag structure. And so the skeletal structure only shows us the carbon atoms. Each one of these points, or vertices, is a carbon atom. And the skeletal structure only shows us how the carbon atoms are connected. It doesn't show us explicitly how many hydrogens are on each one of these carbon atoms. So in a skeletal structure, we actually don't draw all the hydrogens. And so we know that this carbon atom, because it's a vertex, right, is bound to one other carbon atom, and that's explicitly shown here by this bond. However, since we have one bond taken up here, I know that the other 3 bonds have to be to hydrogen, because in the skeletal structure rules, we never draw hydrogens. And so if we just see a point, like for example here, we know that the remaining valences needed for carbon have to be made up by hydrogen. So it works real quick. On a piece of paper, I can just quickly draw the skeletal structure of hexane and have it in place. Now, if you think about cyclohexane, which is a ring structure like this, okay, so 6 carbons in a ring, 12 hydrogen atoms, that would take quite a bit of time to draw. I ask you to draw it now, and you'll see about how much time it takes. However, I can draw this shape, this polygon, real quickly just using a pencil. And each one of these vertices is a carbon atom that is connected to 2 other carbon atoms, right? So if that's a carbon, then it's bound to this carbon and this carbon. And I know that the remaining valences that are available for carbon have to be hydrogens. And so you can see, actually, there are 4 bonds to every carbon atom. And so those hydrogens are there. They're just not explicitly shown. So on these so-called skeletal or bond line drawings, we only show the connections to the carbons, and each vertex is a carbon atom. We do not draw in the hydrogens if and only if those hydrogens are to carbon. If those hydrogens are actually bound to a heteroatom, that is an atom that's not carbon, then we have to draw those in. So for example, if we look at this molecule, so we have 1, 2, 3, 4 carbon atoms, and then an OH on the end. This is known as an alcohol. We'll learn about our functional groups more in the next chapter. I know I'm going to need to have 4 carbons, so there's 1, 2, 3, 4. And that fourth carbon is actually bound to an oxygen atom. Now that oxygen atom is also bound to a hydrogen, and I have to draw that in. If I do not draw that in, it would be incorrect. You have to show the hydrogens to all of the heteroatoms. Now notice in this particular structure too, I'm not showing the hydrogens to carbon, but I'm also not explicitly drawing the electrons on oxygen. Organic chemists quite frequently ignore the electrons that are on the heteroatoms like oxygen, nitrogen, sulfur, etc. You have to know they're there though. Those electrons are in fact there. If you look at chlorocyclohexane, we could draw it like this. Nothing wrong with that. It just takes a little bit of time. But I can quickly draw it shown here. And notice you have to put in Cl for chlorine. You can't just draw a stick. Because if I draw a stick and there's just a point here, that's a carbon atom. But it's not a carbon atom, it's a chlorine, so we actually have to write Cl. And again, notice electron pairs have been omitted. That's just a normal thing that we do in organic chemistry. Okay, so that was really what I wanted to finish up in class today. We will finish this up in on Wednesday with the inverted lecture, so make sure you've watched this before you come to class on Wednesday.